Good? Everyone hear me okay? Hello? That better? Okay. I feel like I'm in a karaoke lounge. Okay, so I'm Dr. Kevin Franke from Brigham Young University. It's a pleasure to be here with you today to give a brief presentation on our progress on a significant and exciting project where we're creating new probabilistic liquefaction triggering and lateral spread displacement hazard maps for Utah County. I want to just give the regards of my collaborators on this project, Dr. Daniel Gillens from Oregon State, his PhD student Maher Sharifi Mood, and then my master's student Jasmine Harper. They're really the magic behind this project, so I'm grateful for their help and wish they could be here today. So, as a background, at least most of you out here have done geotechnical engineering in the state are familiar with maps like these. These maps have been around for a long time. Since, well, they were published in 1994 by Anderson, Dunn, and Kiefer. And these liquefaction hazard maps for the state of Utah have really done a great job and served a great purpose. These maps, when they were developed in the 90s, really were at the time state of the art. They were developed considering probabilistic ground motions. And they had a little bit of geotechnical data considered with them as well, or whatever they could get their hands on. But the real magic that they were able to use with these maps was the correlation to surface geology maps from the Utah Geological Survey. And at the time, they didn't quite know how to quantify the hazard, and so they went ahead and just did these kind of generic descriptors ranging from high all the way down to very low. And as a consulting engineer, then, whenever we would do a new project and we wanted to look at the potential for liquefaction hazard, we would always consult these maps initially. And I certainly remember the days of using these maps and looking at it and saying, oh, wow, we're in a moderate area. But I didn't really know what that meant. It just meant we were in a moderate area. And that leads to some of the problems of the deficiencies and the reasons why we needed new or improved maps. I think first and foremost, while these maps were developed back in the mid-90s, our understanding about the concepts of liquefaction hazard and lateral spread hazard and other effects associated with liquefaction have really advanced substantially. And a lot of this new understanding is not portrayed or captured in the maps. And as I mentioned before, the use of these vague hazard quantifications, such as high, moderate, low, very low, can really lead to inconsistent interpretations. For instance, how I perceive or what I do with a moderate hazard liquefaction area may be different than what you might do. There really is nothing in writing or not a lot of guidance saying, if you're in this type of mapped area, this is how you should interpret it. And so, in a world today where so much of our design and so many of our decisions are based on predicted performance, having an actual performance metric would be better in today's world. The maps that were developed in the mid-90s were developed with kind of a strange probability level because at that time, the ground motions, or the probabilistic ground motions that are made available by the U.S. Geological Survey were not available back then. They're available today, but not back then. So as a result, the earthquake ground motions that were evaluated or used to develop those maps were developed on something like an exposure period of 100 years, where everything today is based off a 50 or even now a 75-year time frame. So basically what it boils down to is that the hazard level specified or at least inferred by these maps are not compatible with the hazard levels that are required by codes today. It's apples and oranges. And finally, in terms of probabilities, the original maps in the 90s looked at the probabilities of different ground motions, but that's where they drew the line. They really didn't look at the uncertainties associated with liquefaction triggering itself or the uncertainties associated with the hazard. And they didn't really look closely at uncertainties associated with soil properties. They had to make some assumptions and some correlations with engineering geology, but that's about as far as they went. So updated maps really should incorporate all the uncertainties involved, uncertainties in ground motions, uncertainties in the soil properties themselves. And we should be using the modern hazard quantification tools that are available to engineers today. And so all of these deficiencies really led to the scope and the development of this project. Now this project is really a part of a much larger project that's been going on for years now, led by Professor Steve Bartlett at the University of Utah and several of his students, including Mike Olson, who's also at Oregon State University now, Dan Gillens, as we already mentioned, and a few other students who've developed both probabilistic and deterministic or scenario lateral spread maps for a couple of counties in Utah, Salt Lake and Weber. And so those projects have been going on for probably close to 10 years now. But there was a big hole. Everyone realized that, okay, we have maps for Weber County, we have maps for Salt Lake County, but Utah County, which is one of the fastest growing and largest counties and most populous counties along the Wasatch Front, we had nothing. So in 2013, the Utah Liquefaction Advisory Group, which is a group that's organized and administrated by the Utah Geological Survey, got together and they voted to make the probabilistic liquefaction hazard mapping mapping of Utah County, the top research priority. And so with that, we set off to search for funding to complete this project. And fortunately, a lot of the players or those entities that have skin in the game came forward and threw some money at us. So UDOT, of course, is one of those. They have a huge vested interest in Utah County after the I-15 Core project especially. The U.S. Geological Survey, of course, was very, very interested in this, and they wanted to throw some money. And then the Central Utah Water Conservancy District, that has a lot of the canals and the water conveyance systems throughout Utah County, was also interested. So all of these three organizations together jointly funded the development of these maps, and the project kicked off late last year. The scope of the project was to develop probabilistic lateral spread displacement and liquefaction triggering maps at 3 different return periods, 475 years, 1,033, and 2,475. And the goal of the project was to be completed by early 2016. Okay, so that's the background. Now to get to the nitty-gritty. Now, how do we make these maps, and how are they going to be different than the maps that we had in the 1990s? Really, how we approached the problem is we said, what kind of inputs do we need to go into this? We wanted to use real live geotechnical data. And so, of course, collecting standard penetration tests and cone penetration test data would be crucial. And of course, we know using probabilistic ground motions made available by the U.S. Geological Survey is going to be important as well. But there's other things. We can't have a borehole everywhere. I can't just snap my fingers and magically make a borehole appear somewhere. And so in areas where we don't have boreholes, we have to make correlations, rely upon statistics to guide our decisions. So this is where we're going to go back, and we're going to use the lessons learned from Anderson, Dunn, and Kiefer, and we're going to rely upon geology surface maps. But here's one of the neat things that distinguishes this mapping effort, and perhaps, in my opinion, makes this the most advanced probabilistic liquefaction mapping effort that's been done in the world today. The AGRC just late last year made available high-definition aerial LiDAR for the entire Wasatch Front, right in time for the start of our project. And so we were able to use the digital elevation models from this LiDAR data for Utah County to the development of these, at least the lateral spread displacement maps. Now, the most critical aspect of this project was the development of the geotechnical database, and this is what my student Jasmine Harper led. And in order to make this happen, I told Jasmine, and my friend Trent, we were just having a good talk about this. I told Jasmine that this project is going to be more communication and networking than it's going to be actual engineering. Because her job was to go out and to talk to all sorts of entities and to sweet talk them into giving or donating geotechnical borings to our project. Now, if any of you have ever met Jasmine, she's just the sweetest little thing, and has just a wonderful person, and so I knew she was the right person for the job. And she did a great job. Now, of course, UDOT donated as much geotechnical information as they had available for the county, as well as the geological survey. But we were able to approach several municipalities and city governments throughout Utah County, and we were able to obtain all the public borings that were available. But here's the thing that made the difference. Jasmine and some students helping her were able to approach several private companies, probably many of whom are represented in this room, and we were able to get several boring logs donated that way. And one of the principal entities that was able to donate lots of borings to us was the Church of Jesus Christ of Latter-day Saints. If anyone's been down to Utah County, you know that there's a church about on every other corner through the entire county. And as many chapels as we could obtain borings for, we were able to collect. And as you'll see later, that was a very substantial contribution. In total, we were able to collect almost 800 data points for the standard penetration test, which is phenomenal. And we were also pleased to note that because so many of these came from notable geotechnical consultants, as many as 767 of those we were deemed usable, which is good because a lot of times in previous counties we had problems. We didn't feel like the boreholes were logged to the standard that we could rely upon or trust their data. We were also able to get 39 CPT soundings, and so in total we had a lot of data that we could use. This plot just shows the distribution of the different SPT boreholes and what type of geologic unit they were mapped in. Maybe this is a better way to look at it. So instead of just showing the geologic representation, we have the name listed out here. The majority of our borings were, as we might expect, in fine grained lacustrine soils. This is an ancient lake bed, of course, so that wasn't too surprising. We were pleased to see that we also had several borings in this alluvial fan, young material, prime liquefaction material, as well as lacustrine sand. And then spread it through other geologic units. This map over here, all the little dots show location where we had a borehole or a CPT that we're able to use. And you can see that we get a good spread. And I think the thing that differentiates this spread of this database from some of the other counties that were performed, a lot of the other counties had all of the boreholes collected right along the transportation corridors because UDOT was the principal contributor for the geotechnical data on those projects. But as you can see in this map, though we do have a lot following I-15, we also have a lot up here in the residential areas. And that's what we want to see, down here in residential areas. And most of those are the LDS chapels. So that was very, very helpful to us. All right, so what would be a research presentation if I didn't bore you with fancy equations? When we look at lateral spread hazard maps, we're going to look at, we need some sort of way to predict lateral spreading displacement. And the most famous, of course, is the Youd and Bartlett lateral spread procedure. It was later updated by Youd, Hansen, and Bartlett. Gillens and Bartlett last year did some interesting things. They took the same data, but they simplified it drastically, and they got rid of the need to put in a fines content and the needs to put in a mean grain size. And they boil it down to a clean sand equivalent thickness of the liquefiable layer. So it made it easier to use this equation and really more congenial for us to use the equation for this mapping exercise. So Dan Gillens brings this equation to me and says, how can we use this equation to do probabilistic mapping? Based on some research that I did with Dr. Stephen Kramer out of the University of Washington, we said, well, hey, let's break this equation into its two main components. The upper component there that deals with magnitude and source, the site distance from the site to the earthquake fault, all of those have to deal with ground motions. So let's lump those together and let's call those a new term. We're going to call that L. And then all these other parts have to deal with the site itself, so the slope of the ground, the thickness of the liquefiable layer. So everything that has to deal with the geotechnical or topographical features of the site, let's lump those together and we'll call those G. Thus, we can look at the data itself and do a statistical calculation and compute the probability of exceeding some displacement given a value of G and some value of L. And so all we need to do then is use the statistical data that we have, plug it into this probabilistic framework, and off we go. So to give you an idea of L, so again, this is the seismic loading. You got to remember, L doesn't really mean anything. It's not like an acceleration. It's not like a velocity. It's not something that I can take a box out, set it up in the field, and measure. This is just an equation, but it's a proxy for seismic loading. What I have here are seismic hazard curves that show then various return periods for this loading parameter L at 4 select locations throughout Utah County, one in the north quadrant, one in the east quadrant, west quadrant, and south quadrant. And L, as we come to find out, is very, very sensitive to its location relative to the fault. And at very low return periods, we see everything everything above here, it's all pretty close. But then we start to see separation when we get into higher return periods, and this is normal. And so this is one of the neat things about this mapping exercise, is that we're able to capture this in the maps. So to boil down a whole lot of information into a single flow chart, this is what we have. Our mapping procedure for the lateral spread maps is an 11-step process that we go through, and for a given point in our grid across Utah County, we get all the uncertainties, or we randomly select liquefiable thickness from an SPT in those types of geologic soils. And then we randomly select a loading parameter L, and we go through and we do this 10,000 times. So we do a Monte Carlo simulation for every point in our grid. And in our grid, we're moving at 0.05 by 0.05 degree grid across Utah County. So we have several hundreds of points across Utah County. The point is, we're trying to develop a hazard curve for lateral spread displacement, from which, for that grid point, we're going to pull off the displacements for 475, 1033, and 2475. And we're going to work our way across the county to do that. If it looks complicated, good, it is. So finally, let's wrap up, and I'm going to show you just a couple of the outputs from this. The 475-year map, I'm not even going to show you, because the 475-year map tells us that everything is in green. It's hard to see the colors on this, I apologize. But in the 475 years, that's basically telling us that in 475 years, we're predicting less than 0.1 meters of lateral spread displacement across the entire Utah County, which is pretty good news, I think. At 1,033, it's still mostly green, but we're starting to pick up some splotches between the 0.1 and 0.3 meters of displacement in areas we might expect, around the rivers, up in American Fork, following some of the creeks down along the fronts of Orem, where we have some really steep slopes. Things start to get interesting, though, when we get to the 2,500-year return period. So one of the things that's really neat about these maps is the resolution of these maps as compared to the maps that we looked at from the 1990s are a lot higher. Okay. So these maps here are for lateral spread displacement. For liquefaction triggering, we're going to develop similar maps, but it's going to show a factor of safety, so rather than just a displacement. We're in the process of making those maps right now, a similar loop that we're going to go through in our workflow. So let's boil it down to this. These new maps are coming, and you're going to be able to use them. What should you use these new maps for? I think, first of all, it would be very appropriate and good to use these maps for a preliminary consideration of liquefaction hazards, triggering and lateral spread displacement, before you have site-specific geotechnical data. They're going to help guide your preliminary decisions. I think public leaders, emergency preparedness leaders, and just public entities in general will be able to use these maps to guide public policy and help with zoning in a similar way that the current maps are used right now. And then as geotechnical engineers, these maps can help us guide and develop a site exploration plan to have an idea of how many borings we should put in a particular area, how deep we should go. Should we really be looking for the monster liquefaction or not at a particular site? I want to emphasize what you should not use these new maps for. We shouldn't replace a site-specific liquefaction hazard assessment with these maps. You cannot do that. And you should never see geotechnical engineering recommendations coming forward based on these maps alone without some sort of site-specific analysis accompanying them. So in conclusions, these new maps are coming forward for Utah County. We're very excited about them. The lateral spread maps are already completed. We're working on the triggering maps right now, and they should be finished by the end of the year. We'll go through the reviews and get comments and feedback. The final map should be completed by spring of 2016, and we're looking forward to, by this conference next year, rolling the maps out to the general public, so that'll be good. The maps are created on a 0.05 degree grid across Utah County, so it's a very fine grid. They have a great resolution. One of the exciting things is we incorporated LiDAR data in this from the digital elevation models, so these are really top-of-the-line maps. And these maps are going to provide a very powerful resource for you, for the consultants, for UDOT, for public policymakers, for researchers, for everybody. I think these will be a great tool for years to come for engineers here in the state. That's all I have. Thank you. Tom, do you have time for questions? Okay, a couple minutes. In the back, go ahead. Well, up to this point, they're giving us two completely different things. The Anderson, Dunn, and Kiefer maps are a map of liquefaction hazard. And what does that mean? I don't know. It really is more susceptibility and triggering. These maps that I just showed you are lateral spread displacement. So there's going to be a relationship between the two, but they're not going to be the exact same. We are seeing some similarities between where we see some high displacement values versus where their maps show some high values. But in general, my first impression when I looked at the maps was, I thought, wow, there's not enough red. But as we looked at the data, we realized, no, that's what it is. So I think that's good news. To answer that question more fully, I think we're going to have to evaluate the liquefaction triggering maps, which aren't completed yet, and I think those will be a little more apple to apple, and we can probably answer that question better at that time. Yeah, Trent? It really sounds like a great idea, and it would be something that I would be interested in. I haven't really considered it at this time, though. I think as a researcher, I'd have to look at the research value in doing something like that. But certainly, I'm hoping that there are going to be leaders and entities within the engineering community that when these maps become available, will be able to carry a lot of that torch and take that to their municipalities and various governing entities and say, we need to do something with these maps. Because I completely agree with you. Yeah. Jim?
Would you be able to frame any of the criticism that's been expressed about the approach and how you address those?
Boy, that's well, yeah, I could. To be be honest, there's not been a whole lot of criticism raised at this point. I think criticism about the mapping procedure in general, I can point out several. When you rely upon subsurface data, liquefaction is a subsurface phenomenon. And if you don't have subsurface data, how do you map it? And really, that's the challenge. And so collecting as much data as we possibly can is critical and key. And I think we did a great job in this project. The Salt Lake County maps for the Salt Lake project had close to 900 borings, and we were just over 800. So we approached the Salt Lake County, and the Salt Lake County mapping project at the time was hailed as this tremendous triumph in the engineering research community. So we're excited to roll this one out. I think it'll be well received. We try to use statistics to fill in the gaps where we don't have data, but there are limitations to that. So what we try to do is just set the rules and say, this is the right way to use these maps. You got to understand what the maps represent. The one thing that keeps me up at night when I think about these maps is the thought that engineers are going to abuse and misuse these maps. That they'll use the maps to forego an actual liquefaction hazard analysis. They won't do their own liquefaction assessment. They won't do their own calculations, and they'll just rely solely upon what the maps tell them. That terrifies me. That's right. If I could reach across and slap them, I would. But all right. Thank you.